All right, so we've got 3 more talks this morning in this next session. We're going to begin with continuing on thinking in our AI ML theme here, specifically looking at data challenges. And we have Charlie Becker from NCAR OurMiles to come talk to us about those data challenges. Welcome, Charlie.
All right. Well, yeah, thank you so much for having me. My name is Charlie Becker. As mentioned, I'm with NCAR and the Miles Machine Learning Group to talk about data challenges, specifically in the context of the Earth systems and machine learning. I think this talk was relatively challenging to put together because I think we could easily have almost an entire week-long workshop on data challenges within ML, and to try to pick some topics to just talk for 30 minutes is a little bit challenging. So this is by no means a comprehensive talk on the challenges, but it does cover a few different themes that I'll go over and kind of supplement that with some case study material from what our group has been working on. So speaking of our group, this is our Miles team here. I don't have time to kind of go through everyone here, but our current team, Miles and Miles Plus kind of affiliate members, wide variety of kind of domain expertise throughout. We have a lot of the members here today. A few of them are actually teaching some of the courses, the interactive sessions later today. So feel free to pick out some of these people to come by and say hello. And all the work and the case studies here wouldn't be possible without the hard work of all these people. Okay, so to start off, there's many challenges, barriers, and considerations. When it comes to data challenges that can not only affect the performance of our general AI models and the usability and the usefulness of them, but even like the plausibility of them. Right, some of these can't even be, our ideas can't come to fruition. It can't be possible, without these considerations.
I'm going to switch the mic out because it's getting a little bit static.
Check. All right. So we need to carefully think through some of these challenges before we move through with some of our problems, not only for efficiency, so we're not kind of redoing and training models over and over again, but to test the general plausibility to see if our solution is actually going to work or not. I've separated, I kind of picked 4 different themes to talk about today with data challenges. The first one being data sparsity and data quality. I think most people are familiar with, the fact that at least from ground-based observations, data in the environmental sciences is super sparse and not equally distributed at all. We have very few kind of observations, or not nearly enough as to what we would like, right? And a lot of phenomenon happens in between all of these observations. So that's certainly one challenge that needs to be overcome. Of course, we use model data frequently for both input and output, and that kind of helps with the sparsity problem in terms of, if you got a good enough resolution anyways, but that comes with kind of a quality or a bias, right? That the model data is imperfect, right? And so those aren't actual observations, and so there's flaws within that data too, which is kind of an additional, more of a quality-centric challenge. So we'll talk about some of those. The next major challenge is, the undefined or lack of labels, specifically for supervised learning. If we're trying to do a classification problem specifically, you need to have labels. A lot of people learn on the data sets like MNIST or some image-based system that's got maybe cats and dogs or other animals or something like that, where we have the known labels of what digit it is or what animal it is. If we're trying to do that in the earth sciences, the data doesn't automatically come with labels. And so labeling data we'll talk about is very expensive from a human to do this, and so that is a major challenge. If you need to generate thousands, maybe millions of samples with labels to train on, you can imagine the challenge there if we're going to use a human method to label all those. So we'll discuss that. Third, I want to talk about kind of spatial and temporal dependence in general, and kind of autocorrelation between data, which doesn't exist in some domains but is highly common in the earth science domain. Data is just related and correlated spatially when it comes to environmental parameters, and certainly in time as well. And so this has interesting ramifications for evaluation and verification of models, as well as actually kind of splitting regimes, which I kind of mentioned in the previous talks, where you can kind of lead to some overfitting if that's not carefully thought through. So, and the last one, we'll talk about computational challenges. These aren't necessarily, I'd say, unique to the Earth system science. I think this is kind of broad to all of machine learning in general, but there's a whole lot of them, and we'll touch on a few of those. Okay, so with that, let's kind of dive into our first case study kind of sense. This is a product, and a machine learning product to predict winter precipitation type specifically. We're interested in kind of being able to discriminate specifically between like snow, rain, freezing rain, and sleet or ice pellets. These kind of have different hazard impacts, so being able to discriminate between them all is useful, essentially. And so our task is, how can we find some data to be able to actually do this? And as we already said, the observational data, especially for precipitation type, is pretty sparse. And so that's kind of some of our first challenge. But overall, we want to predict make a product that can take some inputs, in this case, numerical weather model input, and predict a frozen precipitation type. So what does this look like? Without going into the details of the model, our input data is modeled gridded data. So we're taking a model from the RAP, or the rapid refresh model here. And we're kind of using modeled soundings, essentially. So your typical sounding variables, the temperature, dew points, and your U and V winds. And we're kind of taking these profiles through the atmosphere as our inputs. Our first data challenge was, to kind of take these from pressure coordinates to height coordinates. Most model data is given in pressure coordinates. But, if you have a feature that's 1,000 millibars, of temperature, and you try to then generalize that over to, say, Boulder, to predict precipitation, well, 1,000 millibars is well beneath the ground surface, and so that's going to have limited usefulness, right? So we need to convert from pressure to height coordinates, which is just one specific challenge that we had to deal with this problem. Our target data is MPing observations. Anyone not familiar with MPing? It's some crowdsourced data from an app that NOAA developed, where you don't have to be a trained forecaster. Anyone can download it, and you can just say, if you observe a specific type of hazardous event or precipitation type, you can just say, yep, it's snowing right now, and it pulls the GPS of wherever you're at and produces a report at that particular location. So you can see that there's probably, you can already imagine a lot of data challenges within this target, and we'll talk about those. In terms of the data sparsity here, if you look at the map on the left, we have essentially MPing observations aggregated over some large period of time for the different precipitation types. You can see that essentially you just get a population map out of it. You're obviously going to get way more observations where people are living and way undersampled in the rural areas. So this is clearly ununiform. It doesn't mean it can't be used, but this is a problem, right? Additionally to that, we have class imbalance, where almost 60% of all of our observations are regular rain, less than 3% are freezing rain, less than 10% are ice pellets. So machine learning models can struggle sometimes if you have imbalanced classes, and there's a variety of techniques you can use to kind of help balance that out. Some of them listed here. You can under or oversample your data points depending on whether you have a whole lot of data or very little data. You can use custom loss functions, or kind of weight your specific classes to kind of push the machine learning model towards a class that may be underrepresented, for example. Okay, so let's kind of talk about the specific data and bias within these data sets here. If we talk about MPing, the first one here is that some users may not be accurately reporting events. The whole next slide is dedicated to that particular point, so I will skip that and come right back to it. The second one, users may be more likely to report an event when it's first happens, so you get some bias there, right? Like if it hasn't snowed for a while and all of a sudden it starts snowing, people are excited, like, yeah, it's snowing, but if it snows for 2.5 days straight, are people really going to consistently be like, every 30 minutes, like, yeah, it's still snowing? Probably not. Not spatially uniform, as we saw in the previous slide. And multiple precipitation types can kind of coexist within the resolution of our input data. So our input RAP soundings, we only have it every 1 hour. You can imagine precipitation type can vary a whole lot in the course of 1 hour. many times, in fact, changing types, precipitating, not precipitating. So we're kind of dependent on that 1 hour and that sounding matching to whatever kind of observation MPing report we choose to map to that. On the RAP or the modeled side, you can get unrealistic. Well, I wouldn't say unrealistic soundings, but you can get overly smooth soundings. Based on the parameterizations and the physics that go into these models. And so, the shapes of these profiles are not going to be the exact same. It's a model data if you had a balloon or a drone and just popped it up and took observations all the way through. So we need to be aware of that. So let's look at that first bullet point. Some users may not be accurately reporting freezing rain or ice pellets specifically. If you look at the figure in blue, it is on the log axis, on the y-axis, but the blue was just like the raw MPing reports that we had. And if you look at the freezing types, you see a whole lot of observations of freezing type where the surface temperature, which is the x-axis, is 20 to 40 degrees Celsius. So probably unlikely that you're seeing frozen precipitation at that particular time. This leads us to believe that there could be some adversarial data in there. Maybe there's just some bad actors throwing in random kind of events at specific times that just don't make sense. So you could be clear and dry. Maybe somebody's just saying it's snow. I think what might even be more interesting is this ice, specifically for ice pellets, is that it could be getting confused with hail. When we dug into the data a little bit more, we saw that there was some convective profiles, some convective soundings that matched up with a whole lot of sleets or ice pellet reports. And then when we kind of briefly looked at the actual app, sure enough, in the app, it's actually listed as ice pellets and not sleets. And hail is like a whole separate section, right? So as an untrained person that hasn't grown up in meteorology, I honestly can't blame somebody if they saw it was hailing and just went to the precip real quick, saw ice pellets and clicked it. I probably couldn't blame them. So we did some manual QC on this. That's the data in the black, and we just took the wet bulb temperature and kind of did various thresholds of filtering it and just got rid of the data over a certain threshold. In this case, I think it was 3 or 5 degrees or something. And this, I'm not going to show any results, but I'll just say that this dramatically improved the performance of our model here. So a data consideration that helped us out significantly. A quick case study number 2. This is another model that we had where we were using kind of emulating surface energy flux at the ground level, and through a high resolution model, and it was an observational based trained model. And so we had an eddy flux tower in Idaho that we trained all the data from, but that was our only tower that we had. Well, we had access to one other tower, but we did not have access to towers in a variety of different landscapes. And energy flux is highly dependent on the landscape that it's on. So that's what these pictures, derive here. If you're on a coastal versus a desert versus a forest, you get different friction velocities happening because of the wind and the turbulence, different ET rates. And so the energy flux is highly dependent on this. And so if we train data, on one particular type of surface scheme, essentially, can we expect it to generalize across a whole bunch of other ones? And the answer is probably not, right? And so Thomas kind of mentioned this in the last talk, this generalizability problem. And this figure shows that, it did not generalize. You can see the clear bias in the different landscapes where you want everything to be on the one-to-one line here, and it's not other than the data that it was trained on, which was this Idaho flux tower set. So in this case, what we did, we just trained a bias correction model. So we literally have now like a chain of neural networks. This one is just a very simple one, but we generated the training data directly from our new surface layer model, right, with different parameterizations, different surface friction levels, different schemes, and then we just map that to the output of the original model. So now we have a chain of models to fix this bias correction, and it actually worked out really nice for us. Okay, so let's go on to theme number 2, this undefined or lack of labels. As opposed to ground-based observations where we don't, we have very limited, sparse data, remotely sensed data, specifically from satellite data. We got a whole lot of it that's coming in every second. We get a bunch of it, and almost all of it is unlabeled. Doesn't mean it's not useful, but if we're going down a supervised learning pathway, we need to figure out a way to provide some labels to this. And hand labeling specifically is really demanding, time-wise. It's demanding, I think, even for trivial tasks, whether you could just take anyone in the general population and say, is this a cat or a dog? It still takes a lot of time, even though that's not that hard to discriminate, right? But in the earth sciences, not only do you need the time, a lot of times you need a domain expert, to actually do it. And then furthermore, you don't necessarily, it's not as clear. Not everything's just a clear, case. There's a lot of borderline cases as to what we should label something. And this next case study kind of highlights that, right? Where we're trying to use ML for convective storm mode. So convective storm mode is, stuff like squall lines versus supercells versus kind of a more disorganized kind of system here. In this particular case, we had 5 different domain experts hand label, over 1,000 different storms. And you do not get consensus on a lot of storms. You see consensus in this top left one here, but all the other ones, you have varying consensus from all these domain experts, right? So what is your labeling scheme in this case, right? Do you just do you average them out and say whichever one had the most? Do you throw away that data if there's not enough consensus? Do you there's a variety of different things you can choose to do here, but none of them are obvious, and there's no golden rule as to what you should do for this. So semi-supervised learning is another approach that we kind of experimented with. It kind of allowed us to bulk label some stuff without, with very minimal human intervention, which is kind of cool, and it worked for us. So I'll walk you through that really quickly. I'm not going to go through this model in too much detail, but this is a model that we used patches of numerical weather model data as our inputs, and we're using a convolutional neural network, which is just a type of network that happens to do well with like spatial images, essentially. And in this case, because we didn't have labels, we trained it on a proxy output. And so this proxy output was just a couple of different parameters that were attributes of the actual storm itself, right? So maybe some geometry, like how long is it? Does it have updraft helicity, above a certain threshold or something? So we picked a couple of things that we thought would kind of map somewhat to the convective mode. And so we bottleneck everything into this latent vector, which is just a layer in a neural network. And we don't care about the predictions, right? But we care about the information that's in this latent vector. And so we pull that out and just cluster it, which is kind of an unsupervised approach. And so we cluster it into different clusters and then kind of run those clusters onto our initial training data. And we're hoping that those clusters represent a specific type of storm mode is the goal here. And so here's an example of a widget that we built to kind of help do this bulk labeling. So these are all images of a specific cluster as we move through. This cluster looks like it's a linear system, so we just label it as QLCS or linear. This one looks disorganized. This one looks supercellular. So it's just taking sample images from each cluster as we move through, and then a human can just roll through all the different clusters, which in this case there was like 25 of them, I think, and just label them, and it applies that label to the entire data set, right? So essentially now you have a way of, labeling millions or, enormous amounts of data in like 5 minutes or something, as opposed to, God only knows how many hours it would take to do that by hand. So that's one kind of effective approach that we found to do that. Theme number 3, the spatial and temporal dependence. That we kind of talked about that's present in environmental data, specifically this autocorrelation. This is already kind of mentioned, I think, in a couple of different talks. I think Skylar's talk kind of talked about this training scheme where, again, in these models that a lot of us learn on, people just say, oh, take your training data and just randomly take 80% of it and randomly take 20% of it, for testing or something like that. That can lead to wonky results, undesirable and highly overfit results in environmental data for the reasons that were kind of already described, right? Essentially, if you're, I don't know, if you've got some data point in time, at multiple hours in a row, and you're splitting, you've got hour 3 and hour 4 and hour 5, and hour 3 is a part of your, let's say hour 3 and hour 5 are part of your training data set, and hour 4 is a part of your testing data set. They're so correlated, they're so linked, the data is very, very similar. So essentially you're kind of mapping too much information from your training set onto your testing set. And so you'll end up getting good verification and results on that holdout set, but you go to apply it to actual brand new data that's not either real test data or just new test cases, going in the future, like a real-time project or something, you're going to see really poor performance as a result because you've overfit your model. So that's one kind of strategy to to do that, and as talked about, splitting it by year or longer chunks of time, also keeping in mind that this exists in space and not time as well. So if you have different stations or something, you might consider the correlation, the similarityness between different ground-based stations, and make sure that you properly kind of map those into different sets before splitting. XAI, or explainable AI, is something that is also dealt with. Correlated kind of inputs and features can have a dramatic impact on this. I'm not going to go into too much detail in the figure here, but generally speaking, this is for that P-type model. If we go back to that, our soundings, we had those soundings, right, as our inputs, and we've got each feature is like, let's say, temperature at the surface, and then another input would be temperature at 250 meters, then temperature at 500 meters. Those are expectedly going to be pretty correlated, right? Like we still want to keep all those individual features, but they're likely highly correlated. Where a lot of these explainable AI methods, the way that they operate is, well, let's hold all of the features static and just vary one as we go through and do something to the model and kind of see how that changes. Well, if you have a bunch of correlated features, it's going to be really hard to see the actual result of that one feature if it's highly correlated with other ones. So there's a variety of XAI techniques that we're kind of trying to experiment with, as far as grouping different variables together for XAI, doing some unique feature engineering, which was also kind of previously mentioned, of maybe trying to eliminate the correlation in the data itself by engineering new features. So this is a space that I think needs some further development in. And let's talk real quickly about some evaluation. This is a cool figure from Ryan Lagerquist, doing pixel-wise kind of evaluation of a machine learning model, which is pretty common, I think, in the Earth system sciences. And this figure on the right shows, I think, like a frontal system of some sort. And let's say that the pink is the truth data, and let's say the gray is the predictions that came out of the model. You'll see that they actually don't overlap at all, right? So if you did an accuracy, was your metric to look at this, your model would have an accuracy of 0%. It would be like, you have the worst model possible, essentially, right, with 0%. When in reality, that's an awesome forecast, probably, right? Like spatially, yeah, it's off just a little bit. The shape is right, the width is right. Like that's probably a really good forecast, right? So we need to think carefully. How do we go about verifying and evaluating, in space and time when things are correlated? And so there's different evaluation metrics, there's different even loss functions that can kind of take this spatial features into account, and different ways to actually deal with that. So lastly, let's talk about computational challenges. Not everyone has the proper resources to create the system that they desire, right? Maybe someone wants to build a huge model, or even not huge, maybe just even a smallish or medium-sized model. They can't, the data size can't fit on your laptop itself. What do you do, right? Not everyone has access to the state-of-the-art computing cluster, or maybe they do, and it's really hard to find a way in because it's just too many users. I think there's a lot of challenges here, and cloud computing is helping solve this hardware problem, I think. But this comes with the drawback. It requires a lot of money, and also related to the money is these careful considerations for usage and storage, right? Where you don't necessarily have to take be as diligent with those considerations if you have your own home cluster per se, but if you're using all the time and retraining over and over again on a cloud system, the cost could certainly add up, right? And so this is a potential challenge. For really big data, advanced parallelization techniques are often required, but not really familiar to domain scientists. Most of us are not trained as computer scientists. We're not trained to be able to program on GPUs per se, and kind of get into the lower level CUDA stuff, and even the machine learning modules sometimes to do a custom model of what you want to do can require some pretty heavy lifting on the computational kind of knowledge side of things. This particular image came from a holographic viewer that was flown into a cloud and kind of taking holographic images of water droplet particle distributions in a cloud. And each holographic image here is 5,000 by over 3,000 pixels in width and length, right? I think that's 15 million plus pixels per image, and we have a whole lot of image. Like this takes an enormous amount of computational power to get the I/O to even like build a batch for training per se. Like this is a non-trivial task, right? And so just the knowledge of that can be a barrier for a lot of people in this field in general. And I think this is also where interdisciplinary kind of help and work can really benefit the field in general. One more time is real-time inference. If you have a real-time product, right? I mean, there's some products that are just kind of meant for, we do machine learning for research, endpoints, but sometimes we do want to take that, research and put it into an operational product per se. Well, your product, we need to actually have a model that is capable of actually ingesting all of the data fast enough and running, providing inference fast enough to actually be useful, right? If you have a model that takes 55 minutes to load all the data and do a prediction for hourly predictions, right? Like your model is essentially useful, or I'm sorry, useless, in this particular case. We actually literally just ran into this problem. This is the precipitation, problem again. Where we had a model, our best model that we kind of hyperparameter optimized, ended up being a really wide and a really deep network, and it ended up being infeasible to run that, in real time. So we actually had to reduce the size of the model, take a small performance hit as a result, because we actually needed to run this in a reasonable time, to make it useful. And lastly, I just want to most, as also mentioned, most weather and climate models are written still currently in Fortran. That's probably not going to change anytime in the super near future. But there's a lot of work to be done of kind of integrating machine learning with Fortran in these climate models, right? In this hybrid approach, maybe taking some parameterizations of different schemes and using ML to do that instead of some basic statistical parameterizations, which a lot of models use right now. But there's not, a consensus at all how to best, integrate the two at all. Some people just write up the neural network from scratch in Fortran, which is effective, but not really. If you decide to change the architecture or something like that, it's not generalizable at all. Calling Python from Fortran has some speed challenges, also compiling issues. This is a very non-trivial problem to solve here. So this is a definite challenge with no consensus yet. So we'll see where the field goes with this one. So with that, I'll just say that Earth system data is very complex. I also think that's what makes it fun. Everyone else already kind of mentioned, right? Most of the work is in dealing with the data. Modeling is a small kind of percentage of the time in comparison. But I think that dealing with these data challenges, at least to me, I think is part of the fun. And careful consideration needs to be made, I think, ahead of time to make this to move smoothly and kind of produce an efficient and good product overall. So with that, I'll stop and take questions. Thanks.
Well, this talk didn't just perfectly fit into the theme of data at this workshop. So questions for Charlie?
Yeah, I had a question about the sparsity. And that map, would that map be able to visually represent sparsity? Because I come from a place that has no data being collected, but nobody knows about it. Nobody understands it.
Sure.
And so they do these models, right, to just interpolate and
sure.
So it's really
it's a problem, right? So it's like I think that it doesn't necessarily, in my opinion, I guess you don't necessarily need to have data at every single location at the exact same sample, but what you need is data at a location like that that's similar enough to that, right? Which there may or may not be, right? There may be some locations where everything is too different, and you're just never going to be able to capture that and generalize to that because you just don't have any data there. But I think that part of the hope in these products where we don't have data is that some other areas capture something that's close enough to it to be able to still do a realistic enough job. And depending on the location, sometimes that happens and sometimes it doesn't.
So I had a question. You mentioned that neighborhood loss functions and evaluation metrics helped with evaluating pixel-wise training. Are there built-in functions to do that in Python that you know of?
As far as the evaluation, I believe I'm sure there are some packages. I'll have to think off the top of my head which ones there are from evaluation, because there's like fraction skill score and some other ones that are built into some packages. I can't think of what package it is off the top of my head. As far as the neighborhood loss functions, probably not. It's still a relatively new area. They might be in there, but I think those are a bit more on the custom side. But I'm happy to point you to some papers that kind of do that stuff.
Where do you see things moving in terms of like equitable compute? Like you were saying, like not everyone has access to like state-of-the-art GPUs or like state-of-the-art high-performance computing clusters, and especially as more people are spinning up and using some of these tools, people become reliant on some of like the free, quote-unquote free, like Google examples or whatever, and then all of a sudden they switch to like a paid model and stuff like that eventually. Like, where do you kind of see that going?
That's a good question. I don't know. I'm a little bit hopeful. I think centers like NCAR and everything that provide the academic community, still a raw computing cluster, that we haven't made the full transition to the cloud yet. Or if there is, if we do decide to do cloud, a lot of grants and everything provide cloud credits and stuff like that I think can be distributed in a way that is more equitable. But I'm hoping this problem, the equity issue, does not get worse before it gets better. But I think I don't know if I have a good feeling as to which direction it's going to go.
All right, let's thank Charlie.